Hello, everyone. My name is Ethan Donald with Tri-D Technologies and ExactFlat Software. I'd like to welcome you to the webinar today. So let me reiterate, thank you very much for attending our webinar today on how to make better marine canvas faster in 3 easy steps. And we know that the participants in this webinar are marine canvas professionals. So we're going to cover a lot of what we're going to do today at a high-level workflow. The presentation will take about 30 to 60 minutes. Once again, my name is Ethan Donald with ExactFlat Software, and I'll be your host and moderator. The workflow we're going to go over today is certainly going to be using a boat cover for marine canvas as an example. However, it applies to all types of soft goods. So if you are doing marine interiors, such as seating, engine covers, and other things like that, even boat hulls, carbon fiber, this workflow will apply to those type of materials as well. If you also do other things like car covers, tent and awning, same thing. This workflow applies, and it can be applicable to helping you make those particular projects faster and easier as well. We are recording this webinar, and it is in listen-only mode, which means that you'll have to use the question feature in your webinar console. If you look at your webinar console, there is a tab that says questions. You can just enter your questions in there. My colleague Mark Jewell and Luke Doransky will be monitoring that, as well as I will be monitoring it myself. As I mentioned, we're going to try and get you back to your desk within 60 minutes, depending on how the questions go. My panelists, again, Luke Doransky, who is a lead developer for ExactFlat, and Mark Jewell. Collectively, they have over 30 years experience in the 3D to 2D flattening space. In fact, Luke is instrumental in developing the product, and Mark is instrumental in leading the team and creating the overall vision for ExactFlat. The two have seen more 3D models and flattened more 3D models than anybody in the world, and they have seen them in every single category you can imagine, from aircraft wings to nose cones to facial reconstruction surgery to specialized materials for artificial organs and transplants, windmill turbines, and all kinds of things in marine. I'm delighted to be joined by two colleagues with the experience that both Mark and Luke have. Our webinar today is going to focus on the core workflow steps, and we've organized them into 3 categories: how to capture 3D geometry, how to create 3D surfaces, and how to create 2D sewing patterns from those 3D surfaces. We are going to be featuring the Proliner by Prodim, which is particularly well suited for doing measurement capture outdoors and for large objects like boat covers and certainly other aspects of the marine product ecosystem. We'll be using Rhino 3D for our 3D CAD, creating surfaces, and we'll be using ExactFlat 3D 2D digital pattern making plugin for Rhino 3D. So those are the products we'll be using. If you have any questions about them, you can certainly ask us, but I will just point out that we will refer the challenging questions to our colleagues at Prodim, and the Rhino questions we'll be able to handle, and ExactFlat questions for sure we'll be able to handle ourselves. In addition to the workflow, we are going to be talking about the best practices associated with capturing 3D geometry, how to convert points to surfaces, how to organize and flatten pattern pieces, if you want to inject strain or tension into your pattern pieces, and how to trace or mark features such as cleats, access points, flaps, flanges, or even zippers. Now, what I'm going to be doing is I'm going to be playing a short video on the first part of our process, which is how to capture geometry in 3D, which covers the Proliner. It's a short video. We want to give you an overview of that process for those of you who haven't seen it. For those of you who have seen it, we'll be talking a little bit later on about best practices, creating symmetry planes and mirroring your surfaces a little bit later. But let me just go ahead. I'm just going to get this video started. To make better marine canvas faster, the process involves 3 easy steps. Step 1 is to capture your geometry. For this, we're going to use the Proliner by Prodim. Step 2 is to convert your Proliner data to 3D surfaces. We'll use Rhino 3D for this task. And lastly, for step 3, we'll convert your 3D surfaces into 2D flat patterns. For this last step, we'll use ExactFlat digital pattern making add-in for Rhino 3D. Let's get on to step 1. Capturing your geometry using the Proliner by Prodim. So what is the Proliner? The Proliner is a device well suited for measuring curved and complex shapes. It also excels at capturing these measurements outdoors and in bright light conditions, regardless of the color or reflectivity of the part you are measuring. So how does it work? Well, the Proliner is a coordinate measuring device, meaning that it captures points in space. These points are captured via a pen-type probe connected to a measuring head. The head can be rotated in every direction. The measuring head is connected to the probe via a cable, which can be stretched out over several meters. A button on the probe is used to mark and capture the relevant points. So how do you use the Proliner? To use the Proliner, you simply set the device up on a tripod, stretch the cable out, and use the probe to capture the points you select as you trace the specific geometry in question. It's not tracing all the dimensions, rather you move the probe from point to point to capture the coordinate in question. The distance of the wire, as well as the orientation of the measuring head, ensure the coordinates are captured accurately. As you can see here, the probe is moved along the surface and points are captured at various intervals. Move the probe, capture a point, and repeat until the full set of needed points are captured. So what's the result? The Proliner captures coordinates in space that accurately reflect their position relative to one another. Here's an example. The next step is to use these points to build 3D surfaces that reflect the exact geometry of the patterns you want to create. For this, we move on to step 2 and use Rhino 3D. Now we're going to get into detail into step 2. And as you can see here, we've got a model which is already captured with many more points. I'm going to hand the presentation over now to my colleague, Luke Naransky, and he will direct the conversion to 3D surfaces and the flattening from 3D to 2D. Luke, if you can take it away, please.
Thank you, Eaton. So we're looking at the wireframe of the model. So this is the result of the Proliner capture. We can see we've got all the different control points for the curves here visible, as well as a number of different features on the back, such as these cleats up at the top here and some cutouts down here. So we're going to be surfacing this data and ultimately flattening it. Then eventually we're going to be tracing these cleats. So if there's any kind of location that you need to mark on your pattern, for whether it's going to be a cutout or a markup for an attachment point or snaps or buttons, you can use the Proliner to capture those locations directly from the boat, and we can transfer those over to the pattern. So to prepare this data for surfacing, we want to have a look at it first, just to make sure that there's no errors with it. So there's already a couple errors on this model, so just as we look around, we want to just select the curves and make sure that your endpoints are all aligned. So when we go to create surfaces from this, we need to make sure that our curves accurately represent the boundaries of the different surfaces. So to fix something like this, it's pretty easy. You can just grab the endpoints here in Rhino. I'm just going to zoom in on that a little bit better. So there's our curve, there's our endpoints over there. So you can just grab the endpoint and drag it over like that. So we would go over the entire model until everything has been fixed, and I've already done this. So we've got our new layer over here called Rebuilt Curves. So this is what it would look like fully fixed. We can now see our endpoints for all of these curves are coincident at the same location right there. So you want to make sure you go over your model and do as much repair work as you can. The better of a job you do with your scanning, the less repair you're going to have to do, and the better of a job you do preparing your curves, the easier it's going to be to surface your model. One other thing I want to point out is I have run a few stringers down from this edge right here down to here, and this is to help control the shape of the surface that's being created between here. So even though we're going to be flattening these 3 panels here as one single piece of material, we are going to be surfacing it as 3 separate surfaces, and that's just to help control the shape so it doesn't have a blowout. So we're going to be using a couple different commands here. There's many different ways to surface in Rhino. Probably the easiest command is the edge surface command. So you can type that into the command line right there, press enter, and using this command you select 3 or 4 edges, and the tool will go ahead and create a surface for you. So it's just a matter of going around all your different edges here and selecting your edges one at a time until you've created your surfaces. So we'll go around, we'll create a few different surfaces here, and then we'll move on to flattening. So it's very easy. You just keep moving along, selecting your edges one at a time, creating your different surfaces. And we're going to join these three curves together. We're going to be surfacing this bottom one down here as one single surface. So we can split and we can join our different curves to give us a curve where it spans the entire edge as much as we need. So once we've joined that curve, we're once again going to use the edge surface command and select the four sides of our surface. And very easily, we'll now create a curve there. For this one right here, this one is one single curve, but we have an edge terminating right there. So we're going to split this curve using that curve, and now we have curves exactly where we need them to create our surface. Actually, we're going to join these two as well. And now we're once again using the edge surface command and just selecting our four sides of our surface. Actually, this one up here, sometimes it will work. I don't actually recommend leaving your curves whole like that, so I would split this up. You're going to get a better result and minimize the chance of any kind of error happening. So I'll split that one up, and we can finish off creating our surfaces. Join these two together. And now that we've split this up, we're going to join it back together so we can surface the top. And now we can direct our attention to the back. And I did miss this one here. This one's joined, so we're going to split that one right there. And check on this one. This one is joined as well, so we are going to split this one as well. We can either select a curve for doing the split, or we can click the point option up here and select the split point on the curve. Both work, but we are going to join these two together so we can do our edge surface of this last little bit here. And we're going to split this one once more right there. Join those two together so we can do this last panel here. So we've surfaced half the boat. At this point, one potential option would be to mirror your geometry. If you did want to mirror your geometry, I'm not going to mirror the whole boat. You do need to make sure that you take steps that to accurately record the mirror plane or the center line of the boat. This boat, that was not done, so we don't have clean symmetry throughout the boat. So if I go to mirror the entire boat, we're not going to get a good result. So it's important that if you do plan on mirroring your boat to save time, you want to make sure you accurately set up and create and digitize the center line, the center plane of your boat. So when you do mirror it, you end up with a very clean mirror. If we were going to mirror it, I'll select this top surface as an example. We can just use the mirror command, and you can pick any of the axes up here as you want as a mirror plane, or what I like to do is I pick 2 reference points. So I'm going to pick the end points for this surface here, and you can very easily mirror any type of geometry that you want just like that.
Luke, I have a quick question for you here before we go on here. Is it necessary to split the line before you surface so that the line you use does not go beyond the surface area?
In most cases, Rhino will succeed if you do not split the line. However, it introduces the possibility of errors coming into your surface, so I always recommend you split the lines. So the curves that you are using for the edge surface command only span the actual edge of the surface. And that's just to minimize the chance of any type of error occurring.
The other thing, Luke, just before you go on to, let's just talk about the symmetry plane. So what we've seen people do to achieve a symmetry plane is they'll take a pen or a Sharpie marker of some kind, put a little bit of painter's tape or masking tape on the front bow, because the front bow, you can generally find the symmetry plane within an acceptable margin of error, and they'll just put a dot at the front bow. Then they'll go measure the back of the boat and get a center line and bisect the back of the boat at its center point. If you capture a point at the front using the Proliner and you capture a point at the back, and these points are always sort of in your like the reference locations for you, that will be an easy way that you can always go back and get a symmetry line. And that way there will be no question about left half and right half and that type of thing. You can surface half the boat, which will take half the time, and just mirror the pieces, and that would be a more productive way of surfacing the complete project. Luke, I'm going to hand it back to you now.
Okay, so I've already surfaced the entire boat, so I'm going to switch over to my already surfaced layer here, so we can see all of the surfaces here. And at this point, we are ready to start preparing the surfaces for flattening. I'm also going to turn off our reference points. We don't need them right now. We will come back to those a little bit later in the workflow, but for now we're going to turn them off. So the first thing we want to do to prepare this for flattening is we want to create a mesh from it. In order to create a mesh, what we are going to do is we're going to rectangle all of our surfaces, and we're just going to join them together. We can use the join command. I've already done this, so it's already joined together, but all you need to do is rectangle select everything, use the join command. You can type in join, or you can click this button right here in the toolbar, and that's going to join all of your surfaces together into one single solid poly surface. The next thing we want to do is use the show edges command. And what this command does is it shows you where you have naked edges. And a naked edge is basically an edge that is not shared by another surface. So ideally, what we would see is only the bottom here where we have the opening of our cover. That's the only edge that's going to be highlighted. If we see any kind of color on the interior of the surface, it means you have a hole or a gap in your surface, and that's a strong indication that the curves used to generate your surfaces did not need a bit of cleanup. There might be a gap between 2 endpoints of a curve, or one of your vertical lines coming down may not have terminated on an endpoint. This can also happen too, going back to your question, Darren, if you have one curve and you forget to split it up, you may end up with naked edges throughout the interior of your model. So as a best practice, you can minimize the risk of having naked edges by making sure you clean up the endpoints of your curves, you split them, and make sure you try to create your surfaces so the curves you select represent the actual boundaries of your surfaces. So we've verified that we don't have any naked edges. We've joined this together. The next step is to create a mesh from our model. To do this, we are going to use the Rhino mesh command. We just type in mesh and press enter. There's a couple different options here. The default controls you're going to see look like this. If you choose to use the default controls, we strongly recommend you just drag the slider over to more polygons, and you can click preview to get a preview of what your mesh is going to look like. In most cases, this is going to give a pretty good flattening. If you want even more control, you can click the detailed controls here. And what I do is I normally just change my minimum initial grid quads to a fairly large value, about 500 for instance. And if we click preview, we can see the difference in the quality of the mesh here. The biggest difference is our mesh is now predominantly quads. We've got very even point spacing between all the vertices of the quads, and we don't have any high aspect ratio triangles. So from an ExactFlat point of view, this is a better quality mesh, and this is what I do here. I just go to detailed controls. All I do is I set the minimum initial grid quads, usually between 2 and 500. You're going to get good results. That's all I do. Click OK, and we have our mesh.
So we have a question here about if there's a gap between meshes. How to handle a gap between meshes?
If there's a gap between your mesh, it's probably because there was a gap between your surfaces. So what I would do is I would delete the mesh, and I would go repair your edge curves, and I would recreate the surface. Okay, so we've got our mesh here. And if we select the mesh, we've only got one mesh. This isn't any good for flattening because we need multiple pattern pieces out of this. So what we're going to do next is we want to explode our mesh. There's a couple different ways to do that. You can use the Rhino explode command. Our preferred method is the ExactFlat explode command. So if you type in EF explode topologically valid, it's that one right there. When you run this command, it's also going to convert all of the quads into triangles, and it's also going to perform basic validation on the mesh to make sure there are no errors. So the explode topologically valid does a bit more than just the regular Rhino explode, so it's our preferred command, but you can use the regular Rhino explode command as well. That's fine. At this point, I'm going to turn back on our cleaned surfaces, or rebuilt, or sorry, curves. And I'm going to use this hide the surfaces, and I'm interested in our guidelines here. When we created a mesh and then exploded everything, due to the way Rhino creates meshes, we sometimes have a couple different meshes that need to be joined together. So I've turned this layer back on just so I can see my edge boundaries. We can see the magenta curve there. So at this point, I'm just going to go around and I'm going to join these different meshes together. And what I like to do is after joining them together, I'm going to hide the mesh, and that just very quickly allows me to see if I missed any kind of mesh. So as I'm going through, I'm going to join meshes together. I'm going to hide the ones that are already joined together. And when I'm done, if there's any meshes left over, I know that I have missed something that it needs a bit more attention. So I'm going to join these two together. Like those. I will join these two meshes together and hide those. These three faces I'm going to join together. I did add a couple stringers here, but this back piece is supposed to be one single piece, so I'm going to join them, hide them. These three here I'm just going to hide because those were separate. That's one single piece there, 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 and there. So I'm going to just hide those. This is supposed to be one piece here, so I'll select all three of these and join those together. And then we're just going to repeat the process for the other side. So we'll make sure join those, hide them. The reason we have difference in triangulation, differences in the mesh, is simply because of the way the curves were constructed. Because the right and left side of the curve network was not perfectly symmetrical, there may have been some kind of inflection point, or and even an area here where we transitioned from a smooth curve to a line right here. So that's why we have a break in the meshes. But it's not a problem. We just select all four and join them together, hide them again. So we'll select these three, join them, hide it. Hide those. And at this point, there shouldn't be any meshes left. And if we've done our job, that's exactly what we have. So now we can use the show command to bring our meshes back. I'm just going to select our surfaces and hide those again. So I'm using the select surface command. I'm also going to select any poly surfaces that we may have, and I'm going to hide those as well. So at this point, we've got our different meshes here that we've joined together, and we are almost ready to start the flattening process. Because we've joined two or more meshes together, we can still actually take these meshes, and we'll rotate around to this one as an example. And if we were to use the explode command, we can still explode that back into its individual meshes. And what's going to happen is if we flatten this as is, ExactFlat's going to do exactly that. It's going to explode it into 4 different meshes. So to prevent that from happening, we want to eliminate all the duplicate vertices along the join boundary, and we can do that using the Weld command. So we just type in Weld. The angle tolerance, you want to make sure that's set to 180 degrees. If it is set to something else, type in 180, press enter, and then just press enter again to perform the weld. So we're actually going to select all of our meshes. I just rectangle select everything, type in Weld, 180, press enter.
If you can just talk a little bit about the differences between Rhino Explode and ExactFlat Explode.
Sure. The only difference is the ExactFlat Explode performs some mesh validation afterwards. So it's going to triangulate the mesh as well as do some validation, whereas the Rhino Explode command just simply explodes them.
And what do you mean by validate? What exactly is being validated?
It's going to check for geometrically degenerate triangles. It will check for topologically degenerate triangles, duplicate triangles, or mesh faces. It's also going to check for disjoint meshes and separate those out. It's going to explode them into individual meshes. So it does basic geometric checks to make sure the mesh is valid and doesn't have any kind of geometric errors in it.
So that would be important then, because if you have a valid mesh, it's going to flatten better than if you have a mesh with some topological issues, correct?
Yes, correct.
Right. And so if just for those who don't know, you mentioned degenerate triangles. Can you just talk a little bit more about what a degenerate triangle is and how it would come about?
Yeah, so a topologically degenerate triangle, you have to have a bit of understanding of how a mesh works. With a mesh, it's represented by a collection of vertices and faces. So typically in a triangular mesh, you'd have 3 vertices that represent one single mesh face. So internally, you've got your list of vertices, and you have a separate list of faces, and the faces simply represent the vertices by index. So let's say you have a mesh with 20 vertices, and one face is represented by vertex 0, 1, and 2. That would be a perfectly acceptable face for that mesh. Let's say you now have another triangle that's represented by vertices 0, 1, and 1. That mesh face is defined where 2 of the vertices are the same index. That's referred to as a topologically degenerate triangle. It's basically going to be a triangle that has 0 surface area, and it's not contributing to the mesh, and it needs to be removed. If you try to perform certain calculations on that face, it's going to create problems. So that's called a topologically degenerate triangle.
It's essentially a triangle with 2 sides.
Well, it has 3 sides, but one side is of 0 length.
Right. Okay. All right.
A geometrically degenerate triangle is very similar. The only difference is with the face list, it might be indices 0, 1, and 2, but vertices 1 and 2 might be coincident, so they share the exact same coordinates in 3D space. So even though it's got 3 unique vertices, when you look at the length of one of the edges, it's got 0 edge length, and again, it's got 0 surface area. So that would be a geometrically degenerate triangle where, again, you've got 2 vertices that are coincident, resulting in a triangle with 0 surface area and one edge that has 0 edge length.
Okay, so we're getting into some sort of deep, conceptual and mathematical water here, but I'm hoping that answers the question about certain, elements of the mesh. We do have another question here, Luke, which is what's the difference between weld vertices as opposed to weld?
I use weld mostly because in earlier versions of Rhino 5, there was an issue where weld vertices simply was not working. So I switched over to weld. I find it's a little easier to use. You don't have to select individual vertices, you just select the mesh. And as long as you set the angle tolerance to 180 degrees, it does the same thing as weld vertices. So we've got our mesh here. And I think we've joined everything. I think we've welded everything. We're just going to weld one more time just to be sure. So angle 180 degrees, press enter, and we're good. So at this point, we are ready to run the Adaptive Remesher. And the Adaptive Remesher, it's going to scan the topology of the mesh. It's going to scan all the vertices, and it's basically going to replace this mesh here with an entirely new mesh that has fewer triangles. And where the triangles are more or less equilateral. So it's going to both decimate the mesh and condition the shape and size of the triangles to be very well suited for flattening with ExactFlat. So we're going to switch over to the Mesh Tools tab of the ExactFlat toolbar, and we're going to use the very last one here. This is the Adaptive Remesher. You just rectangle select everything and press enter, and this is going to start the Adaptive Remesher. The defaults are, in most cases, perfectly fine for your meshes. ExactFlat's going to automatically set the desired or the default tolerances here for the size of your mesh. We're not going to go into high-level detail of exactly how this works, but these are in model units, and these are the maximum allowed distances between whether it's the surface or the boundary of the old mesh and the new mesh. So bigger values here result in bigger triangles. Smaller values here result in more smaller triangles on your mesh. So I'm just going to use default settings here. We're going to click Start, and very quickly we end up with new meshes over top of the original. We can see over here in the report our initial vertex count compared to the estimated new vertex count. And in most cases, we've dramatically reduced the triangle in the vertex count here, which is going to result in faster optimization, faster flattening, and in a lot of cases, it's going to be more accurate. So this looks pretty good. We'll go ahead and click OK. And we just give it a once over, make sure that you haven't eroded any of the fine curvature or detail in your model. But for this, we've got a really good result here. So after running the Adaptive Remesher, we can now start the Flattener. So we're going to switch over to the Tools tab of the ExactFlat toolbar, and we're going to use the very first one here. This is the Flatten tool, and we're just going to rectangle select everything and press Enter. Very quickly, we end up with our 2D unoptimized flat patterns. And at this point, what I like to do is over in the Layers tab over here, I'm going to make the ExactFlat pattern layer the default layer by placing a check mark right there. We're going to hide the model layer. We're also going to hide everything else by turning off the light bulbs. And lastly, right now we're in perspective view. I'm just going to double click that to go back to our 4 viewport layout. We're going to maximize the top view, and we're already in shaded mode here. If you're not in shaded mode, you can just click the down arrow right here, and you can change from wireframe to shaded mode just by clicking on shaded. This is going to allow you to see the color of the mesh, which represents the amount of strain on the mesh, which is your primary indicator of quality and accuracy. So ExactFlat just arranges the pieces in pretty much any order. I'm just going to grab a bunch here, move those to the side. I'm going to grab these 3 over here, move them to the side, and this is going to allow me to zoom in a little bit closer. ExactFlat operates as a 2-stage flattener. The first stage is Pre-Flatteners. So the Pre-Flatteners are algorithms that will go out and search, and they work with the original 3D mesh data, and they're going to take your 3D mesh data and create some kind of unoptimized 2D flat pattern. And that's what we're looking at here. We're looking at the result of a pre-flattener. The second stage is our pattern optimizer. That's the spring tool here. We're going to use this in a little bit later. That's going to use the mechanical properties of the material that you've selected to reduce the triangle and vertex count to as close to 0 as possible. As we look at our pattern, we can see quite a bit of different information here. Most noticeable would be the rainbow colors on the pattern pieces. We use color to represent the amount of strain on the pattern pieces, and that directly correlates to the quality and the accuracy of the pattern. White represents no strain, cyan is up to 5%, green is up to 10%, yellow is 15%, and red is 20% or more. So ideally what we want to see after we finish the entire flattening process is we want all of our pattern pieces to be white. If we see any color on them, that means we've got a bit of strain, and depending on the material you're working with and your project, that strain may be acceptable, or it may be an indication that you might have to split your part up into 2 or more pieces to further reduce that strain. The other thing we can see is on some of these pieces we have a little cross mark right here. So these crosses indicate folds or wrinkles, and I don't know if we're going to be able to see it, but if we zoom in, we can't really see it clearly here, but we'd be able to see some material here on the edge that's basically folded over on top of itself. So if you lay your material down on your cutting table, you take one corner of it and you fold it over. That's what a fold or wrinkle is, and mathematically that's what's happened to these pattern pieces here. So folds and wrinkles are patterning errors. They do need to be fixed, and we can very easily fix them using a pre-flattener. I'm going to use our Smart Fracture pre-flattener for this webinar, but we do have additional pre-flatteners. So this entire group of icons right here are our pre-flatteners. You can use whichever one you want. You can use them as many times as you want and in any order that you want. They all do the exact same thing. They are just different algorithms for taking your 3D model and flattening it down to some kind of 2D unoptimized flat pattern. So as long as you get a flat pattern that doesn't have folds or wrinkles like this right here, and you can also use them to further reduce the strain before sending them to the optimizer. It doesn't matter what the shape of your piece is, so long as you don't have folds or wrinkles. When you run the pattern optimizer here, this is the tool that's always going to give you the same production quality pattern. So you can use any pre-flattener you want as many times as you want in any order. There's no right or wrong way to use them. I'm just going to use Smart Fracture because it works very well for this. And as I click on them, we can see we're pressing the material out, so we're reducing the strain on these pieces here. And more importantly, on these ones down here, when I run the pre-flattener, we can see it's pushing that material and the folds and wrinkles out. So we're using it to remove the folds and wrinkles, as well as further reducing the strain on these pattern pieces here. And we do have one piece here. I'm thinking I may have missed an edge or a mesh when I did my initial flattening. So we'll have a look at our 3D model. We'll find out where this thin strip is supposed to go, and we can just merge this back together with the piece that it's supposed to belong to. We can actually also use our find tool to do that as well. So we're going to finish the flattening or pre-flattening first. Everything's looking pretty good here, and then we're going to find out where that piece is supposed to go, and we're going to merge that back together. So I'm going to take my binocular tool here. This is the find tool. And I'm just going to click on one of the edges and find its neighboring pattern piece. So that's this one right here. Those two, nope, I think it's supposed to go to the other one. So we're going to try the other side, that one right there. And I think probably when I join these back together, I forgot to weld them exactly like I mentioned earlier. So that's why we have ExactFlat exploded these 4 meshes into 4 separate pieces instead of flattening it as one like this. If that happens, you can go back and fix it, or you can just use the ExactFlat delete cut tool here. And I'm just going to click on the edge to delete those pieces, merge them back together. Same thing there, same thing there. So it's not a big deal. That's a pretty easy thing to fix. So you can either go back and repair the mesh and then reflatten, or you can just merge those pieces together. So now that I've removed all the folds and wrinkles, I've removed most of the strain, I'm going to go ahead and run the pattern optimizer. So I'm just going to rectangle select all of our pieces here, press enter, and now we have our pre-spring controls. In most cases, the defaults are just fine. I do have one option on here. It's called Preserve Boundaries. I'm going to turn it off for this project. This setting is useful for some project types, and you may want to experiment with it to see if it works well for your projects, but it will basically prioritize maintaining the perimeter length of your pattern instead of surface area, whereas when this option is off, ExactFlat is going to prioritize maintaining the surface area of your pattern piece instead of perimeter. So it depends on the material you're working with and your project specifications. In most cases, you want to have this off. It's going to optimize faster and in most cases give you a more accurate result. We can also choose the material that we're going to be working with, and I do apologize, I don't think I have any marine canvas in my library today. But we do have an extensive library of materials. There's about 80 different materials here. It is very easy to get your own material into the ExactFlat library. We do partner up with a lab and we can provide contact information for them. They only charge about $30 US per sample, and the turnaround time is usually a couple business days. They will analyze your material for you and send you back an Excel spreadsheet which contains all of the information that you need to create your own material for use within ExactFlat. So it's very easy to get your own material in here. So for this webinar, I'm just going to use cotton here, and we're still going to be able to see the process. We're still going to get very good patterns, and the reason being is most of these surfaces are very near developable. So I'm going to go ahead and click OK, and very quickly ExactFlat is going to start optimizing these pattern pieces. There's quite a bit of different information being displayed here, even though we're going through these pretty quick. The biggest pieces of information to look at would be the average energy density. That's this value right here. And this represents the total amount of energy on your pattern piece after you stretch it back to the original 3D shape. So energy is just a way of saying strain. So the more energy the pattern piece has, the more you're going to have to stretch it to get it fit back to the original 3D shape, which results in more strain. To put that into perspective, if we look down a few lines, we come to our energy density at 1% elongation. So this is how much energy we would expect to have in the pattern if we had to stretch it 1%. So 1% elongation would be roughly 0.4 Newton meters. When we look at the average energy density for this pattern piece here, we're at 0.0002, very, very low. That's telling us that we have, on average, less than 0.1% of strain on the pattern piece. And we can go back and look at all our different pattern pieces here to see how much strain we have, 0.0033. So overall, this is telling me that we have very, very good patterns, and in all cases, we are far below 1% strain on our pattern pieces. The other thing we can look at is the no seam stretch error. So this is a report of how much the perimeter length of the 2D pattern piece is deviated compared to the perimeter length of the 3D model piece. So again, this is in model units, in this case inches. So this perimeter length is deviated by 0.07 inches, which is very, very small. In most cases, your material will very easily stretch to overcome that, that error. I did mention previously that we do have a preserve boundaries option, so if you turned that option on, it would further reduce this value here at the expense of increasing the strain on the pattern piece, usually because the pattern piece is going to be shrinking even more, so you're adding more strain to preserve the 2D boundary. So in most cases, leaving preserve boundaries off is the better option, and you're still going to get a very, very good no seam stretch error. So we'll go ahead, we'll click OK, and at this point we have finished the pattern optimizer, so we have our production quality patterns here. It's very advantageous at this point to arrange your patterns so they're easier to work with. So I'm going to grab one piece that's very recognizable. This is the top of the boat here, so I'm going to grab that. I'm just going to pull it up, and I'm just going to rotate the piece so it is perfectly horizontal and a little bit easier to work with. Next, I can use our find tool. We've already seen this as I was repairing these pieces down here, but we're going to use it again, and I'm going to use it to find the neighboring pattern pieces. So I'm just clicking on my pattern pieces one at a time here until I can find all my different pieces. And there we go. I might clean that up a little bit more. So I'm going to drag this piece down here, just like that, and I'm going to rerun the find tool just to clean this up a little bit more so we've got a bit more separation. And maybe what I'll do is I'm just going to use it on these pieces like that. And then we've got these pieces down here. So very quickly, very easily, I'm finding all my neighboring pattern pieces. without much effort. And this makes it a lot easier when adding things like notches to actually orient the pattern pieces so we know exactly where they go. We've got those two pieces, and then lastly, we've got these three pieces down here. So I believe this was the bottom, so we'll use the find tool on that. And we just create our stack like that and bring it up there. So that would go somewhere in there like that. These would go out here to the sides a bit more, and then these three just fit right up in there. So at this point, we can go ahead and we can start doing things like adding notches or alignment markings. So if we wanted to add notches to the pattern pieces, we can easily do that using the ExactFlat notch tag tool. That's this one right here. So I'll start up the tool. I've got mine configured, so the text that's going to be created is just simply a number. You can change this to whatever you want. And I'm just going to add simple slit notches here, and they're going to have a length of 1 inch. So I'll go ahead, I'll click the add button, and as we start clicking on the edge, we can click on any of these vertices here, and when we click, we're going to add a notch where we clicked, as well as on the neighboring piece here. So you can add as many notches or as few notches as you want. You can add them to as many pieces as you want. And you can use these as actual notches, or you can just use them as alignment markings. So later on in the process, when we create our DXF, these notches are all going to be output to a separate layer, which means you can assign either a blade tool or a pen tool to that layer to do exactly what you want. We can also notch right on the corners of the pattern pieces, and in this case, it's going to add 3 different notches. So that's telling us that this corner point is coincident with that vertex, as well as that vertex right there, which makes it a little bit easier when sewing large spans like this. You know exactly where all your different pieces come together and sew on that edge. We also had a number of curves on the original 3D model that we wanted to flatten down to the 2D pattern. So at this point, I'm going to bring back our 3D model. I'm also going to turn our clean curves back on, or our rebuilt curves here. We're going to go back to our perspective viewport. So we've got our model right there, and if we orbit around to the back, we can see we've got our different cleats here. So we can flatten those down to the 2D pattern using the trace tool. That's this one right here. And I'm just going to select all the curves for this pattern piece here. This one was split up into a couple of different curves. And we're going to select our target piece here. And we're just going to drag the slider all the way to the left. This is going to give us the highest quality trace, and click OK. And just like that, that's how we would map that. So now we can see those cleats have been flattened down to the 2D pattern pieces.
And let me just interrupt. There was a question with respect to how you would add zippers and other markings, and that would be, so if you were to put a zipper, like say a zipper line across something, one of those pattern pieces, you do it the same way, correct?
Yeah, if you want to pen the entire zipper line, you could do that. Some people, they only like to mark the start and the stop of the zipper, so you could mark the location of that zipper. You could either use a notch, you could use a different type of notch or different length of notch, or you could use a trace. You could trace a point or a rectangle or something on there. There's lots of different ways, and it really depends on your preference.
And if you were to make a window, for example, say in the back surface, like you wanted to cut out a small window on the front surface, you could, again, project lines onto the surface and then use the ExactFlat trace command and trace the marking from 3D to 2D in the way that you just did.
Yep, you could absolutely do that.
Okay, so let's just talk about windows for a second, because you have a choice of doing them in 3D, or you can do them in 2D, correct?
Correct, yes.
All right, so the process then essentially is you first of all sketch whatever feature you want, whether it be a cleat or an access point or whatever it might be, onto the surface. And then you have the option of flattening that from 3D to 2D by tracing that feature onto the pattern piece. And you don't even have to go back and reflatten it. It's just automatically there. I wonder if you can just show people again, Luke, just using the cleat, the access point for the cleat down at the bottom left there, the blue one, because this is a question that's come up in the panel here, and I just want to make sure everybody understands at least this option for creating it.
Yeah, so I'll use this one because I haven't traced this yet. You just click the trace button here. You select the curve that you want to flatten, press enter. You select the target. In this case, it's going to be that mesh right there. Press enter. Drag your slider all the way to the left and press OK.
And then that will be traced onto your 2D pattern. Yeah, and that could be either for a cutout, or it could just be a pen location for marking something, or whatever you have in mind. The other thing too, Luke, I just want to address is another question that came up from Emmanuel here, and he's talking about these surfaces being relatively simple surfaces from point to point, and the fact that this is metal, that these are not metal surfaces, they're fabric, and they'll deflect and they'll stretch, and some of the surfaces will be non-developable. I'd like to address this question first by talking about the differences between what ExactFlat is doing from a flattening perspective and what Rhino does, because I think that's a question on people's mind. Can you just talk a little bit about that?
So ExactFlat will flatten non-developable surfaces basically by trying to minimize the average energy density across the entire surface to as close to zero as possible. I don't have specifics on how a squish and smash and unroll surface work in Rhino, so I can't compare them too much. But what I can say is that ExactFlat will flatten any type of surface, whether it's developable or non-developable, and its goal is to minimize the energy density as close to zero as possible. So the accuracy of that depends entirely on how well you prepare your model and where you place your splits and relief cuts and darts on your part. So there's a lot of different tools there that will help you get the best pattern possible using ExactFlat.
And the other thing too, as Luke did mention, we do incorporate the material properties of the particular fabric in question. If there's a material that you're using that's not in our library, we have an easy way for you to get it tested and input into the library. And the material properties add an additional element of precision. And then there's ways to fine tune your pattern. So I want to bring up one of those right now, and it's using the target strain. So if we can just go to that, Luke, if we can just maybe pull up the 3D model, select one of the long surfaces there at the front of the boat, and then just talk about what the target strain feature is, how do we use it, and what result, like what it will do for your desired intent, like whether you want your piece longer or shorter.
Sure. So global target strain is just a way of artificially introducing strain into your pattern. So the goal of ExactFlat normally is to minimize strain. So when we look at our pattern here, they're predominantly white. And if I actually go here, I can turn off our edge highlight, and this allows us to much better, easier see the color. And as we look, we can see a few areas where we have very light cyan, but overall, the pattern pieces are almost completely white, and that tells us that we have virtually no strain on our pattern pieces. In some instances, you may want a bit of strain in the pattern pieces, and that can be useful for removing sag that may occur on your pattern. In other industries, that may be useful for things like medical compression bandages. You might want to actually apply or have your compression stocking apply pressure to the limb. Or in things like paint protection film, often the installers, they need to stretch the film to get better adhesion, and you can use global target strain to achieve that. The way it works is you specify a grain direction on your pattern piece. I'm going to turn up my edge highlight back on for this, and we'll switch back to the Tools tab. We can assign a grain line to the pattern pieces, and I'm just going to pick an edge or a mesh edge along the side of the piece here. And when we assign a grain line, we have this option here, global target strain. If you don't want global target strain, you don't have to change anything, just click OK, and that's going to create your grain line. If you do want global target strain, place a check mark in the box here and give it a strain value. So for the purpose of this demo, I'm just going to use about 3% strain. And when we re-optimize this piece here, we would expect to see it turn more cyan, telling us that we have about 3% strain on it. So we can apply strain in both the principal direction, and that's principal strain, and that is strain in the direction of the grain edge. We can also apply transverse strain, so that would be perpendicular to the principal direction. So transverse would be from side to side, principal would be from top to bottom in the case of this part right here. So I'm going to apply about 3% principal strain, which is basically going to compress the pattern piece from top to bottom. So I have to stretch it by 3% to get it to fit back onto the original shape. So I'll go ahead, click OK there. And now because I've added a grain line with global target strain, I'm going to re-optimize this pattern piece here. I'm going to use the exact same settings. And what's going to happen is ExactFlat is first going to optimize to as little strain as possible. Then as the very last step, it's going to apply the global target strain to the piece. So afterwards, now we can see this piece here in particular is cyan. That's telling us that we've got about 3% strain. And if we try to align our piece here, we can very obviously see that this edge is shorter than the other, and that's because we've compressed it to introduce that 3% strain.
Okay, thanks. So the most obvious application here are for long pieces that have a long span that are going to be under the effects of gravity and deflect downwards, and you don't want that to happen. You want it to have a nice, taut, finished, straight edge. You can apply a strain like Luke just did. You can also apply a negative strain, which would add excess material. So if you think something is going to be a little tight, say for example a snap location or something like that, you don't want to have to unnecessarily pull it or strain it too tight. You can apply what we call negative strain, which is essentially the lengthening of the material. And as a marine canvas professional, we know that you guys deal with this all the time, so we won't talk too much about it. But suffice to say that this is a feature and a tool that you can use to make your marine canvas more in line with your desired intent. There is a question also, Luke, from Margit, and the question is, if you wanted to move a seam, or if you want to create new ones in addition to the ones you already have, when do you do that? At what point of the process do you do it?
So typically all of your seams are going to be created when you're doing the surfacing steps. Seams are usually located along the edges of your surfaces, so that would be the correct place to do it. If you've gone through the entire flattening process and you realize that you absolutely do need to split another piece in half, you do need to add another seam, we do have a couple tools, but we strongly recommend that you do all of your seam placement before you even create your mesh. It's going to be much easier to split up a surface and create your new seams with surface edges than it is to use the ExactFlat tools. That said, if you did need to split a piece, you have a couple options. Probably the most versatile option would be the plane cutter here. And in 2D, this allows you to pick a starting edge. As we move our mouse around, we can see our cutting curve right there. And I can pick an end point right there, and ExactFlat will just cut it along that cutting path. So again, if you absolutely need to do it in ExactFlat, you can use a plane cutter, but we strongly recommend that you build in all your seams into your 3D model before you even create the mesh.
Next question, Luke. Thank you for that. Is that there are situations where there's going to be darts required, and we didn't talk about darts. You want to just talk a little bit about how we would put darts in, either before flattening or after flattening?
So depending on the shape and the length of the dart, there's a number of tools. Again, the best one would just be the plane cutter here. So let's, we don't really have a good example over here. This is probably the highest strained piece, but let's say we wanted to add a dart on this piece here. I do apologize, I'm not a marine professional, so I'm not sure where your darts would normally go. We use the exact same tool that we used to split our piece in half, only this time we don't split it all the way half. So now I've added a dart right there, and if I were to re-optimize this piece here, we are going to see a change in that cut profile. In this case, because this is probably not where you put a dart, we're actually seeing the two halves of the material converge on one another, so we have an overlap there. But if you were to place a dart in an area of high sag, you would absolutely see this dart open up, and you would see material being removed. If you wanted to add a larger dart, you can actually cut a physical piece of material out. So again, I'm going to use the plane cutter here. I'm going to pick that endpoint and I'm going to physically cut a piece of material out. So now I've removed a chunk of material there, and when I go and re-optimize, we will once again end up with a slightly different pattern piece that is conforming to the cuts that are the darts that have been made.
Okay, and could you just talk a little bit about the strain map and its utility in finding locations for darts?
Yeah, so as I previously mentioned, we use color to represent the amount of strain on the pattern pieces, the quality and accuracy of the flat pattern. So white represents no strain, cyan is up to 5%, green is up to 10%, yellow is 15%, and red is 20% or more. So just looking at this pattern piece here, most of our pieces are white. If we turn off our edge highlight, it makes it a little bit easier to see the strain maps. We can see a little bit of cyan around the edges here on these pieces here. And because we've applied 5 or 3% global target strain on this one, we've got a lot more cyan on this piece here. So using that, you can just look at your pattern to see where you would expect there to be some strain. So on these ones here, we would expect these panels, these edges, these seams to be a little more on the tight side, whereas these ones draping down off the side would be a little more loose. You can view strain on your 3D model. So let's bring back our 3D model. We'll go back to perspective viewport. And if we look at our 3D model, we can see all the changes that we've made in terms of notches, darts, relief cuts. We can see all these changes on the model, and specifically we can see where the strain would be projected to be on the 3D model. So you can use this before you even cut out material to get a sense for where your expected high strain or high sag areas would be, and then you can just easily place a relief cut in that area.
All right, thank you for that, Luke. I've actually put a link to 2 videos in the chat. There was a question from Richard, and if you want to know more about darts or relief cuts or this types of thing, it's a pretty common part of the workflow with ExactFlat, and any type of dart and any type of relief cut is possible. The 2 videos may be helpful for you to understand. This is necessarily a simple model because we're trying to get through this in a reasonable amount of time, and as you know, making great marine canvas is not a trivial exercise. It takes a lot of expertise to do it and do it right. So we're trying to cover more of the workflow at a conceptual level versus like a tutorial that is hands-on tutorial. That being said, we're happy to give you guys more information. If you want to know more, just reach out to us. We're happy to accommodate. You want to maybe just wrap this up and show how we create an export file, and then we can take any additional questions that may be floating around still.
Sure. So we can export our pattern as a DXF using this icon right here. It's the DXF exporter. You just click the icon and you give your pattern a name. I'm going to call it pattern, and that will create a DXF. So I'm just going to drag that file back onto our document here and import it, and we can very easily see the pattern that was created for that file. So on the pattern, we can see our red cut line. If we zoom in a bit, we can see our green notches that we've created. We can see the split line right there that we placed. Down here, we can see the dart that we added. This one you would probably discard. And over here, we can see all of the traces, the cleats and the cutouts that we've added. If we look at the structure of the DXF, everything comes in on different layers. So our cut line is on a separate layer from the grain line, which is separate from the notches, the notch tags, and the trace line. Everything's on different layers.
So the one thing we didn't do, Luke, is put a seam allowance on. If you can just maybe repeat that process and just go, just add an additional step of a seam allowance.
Sure, so we can specify a global seam allowance in the ExactFlat options. So we're going to expand the ExactFlat options and go to DXF export. And down here, we can set the seam allowance. So depending on your needs, you might have a 1/4 inch seam allowance or more or less. You just enter in the however much seam allowance you want, and then when you export your DXF again, we'll call this one pattern 2. ExactFlat is going to add a global seam allowance around the entire perimeter of the pattern piece. So now if we zoom in, we can see we've got our seam allowance there. And if we measure the distance between our seam line and our cut line, we've got a 1/4 inch seam allowance.
Okay, so that pretty much concludes the workflow, at least the 3 main steps that I mentioned before of how to capture geometry, how to convert your Proliner data, which are points and curves, into 3D surfaces, and then how to create 2D patterns going from 3D to 2D flattening. There is a question here about the tightness or looseness of this particular cover. Remember, the cover has been digitized on the surface of the boat. So when the boat was actually, when the Proliner was used for the boat, the points were captured right on the surface of the boat. So it'll be tight fitting to where those points were captured. The 3D to 2D algorithms will be a faithful reproduction of the patterns that are needed, such that when the final project is sewn together, it'll fit exactly like a glove. And as we mentioned before, we have a lot of experience in a lot of different industries with that demand high accuracy. And in fact, if you get into your car after this day of work and you drive home, you'll notice on your dashboard there'll be a texture. Those textures are made with ExactFlat. The mold requirements are typically to 1/1000th of an inch, and about 80% of the new cars that are produced in the world, these are passenger vehicles, not new cars meaning light passenger vehicles like trucks and cars, are made with ExactFlat on their dashboard, their center consoles, their A-pillars and things like that. So we feel very confident that you guys will be happy with the level of accuracy, but you'll need to see it for yourself. With respect to checking the fit, we have a number of options that are available. First of all, you can measure the edge perimeter in Rhino in 3D and 2D, and you can see to what extent the 3D edge matches the 2D edge. Second thing is you can measure the surface area of the pattern in 3D and 2D. And if there's a high correlation between the surface area in 3D and 2D, then you know you have a very accurate pattern edge. And in fact, what Luke was mentioning before when he talked about the energy density, you can imagine a piece of cloth like a spring. When you stretch the cloth, it'll snap back into place. More stretchy cloths will have more of that, less stretchy will have less of that. But when you have an energy density that's close to 0, you know you have a very accurate pattern piece. So before you even get to sewing, you'll be able to predict the fit. The Proliner is a very accurate measuring device. Those of you who have used it, you know this already. Those of you who haven't, you can talk to those of you who, some of your colleagues who do use it. It is more than sufficient from an accuracy perspective. Now, we don't work for Proliner, but we have experience with the tool, and it'll get the job done. We can vouch for that. So you have a variety of options, Emmanuel, with respect to checking the accuracy. Excuse me. In addition, we talked about the target strain, which you can dial in tension, and with the target strain, you can either relax the pattern or make it more tense and so on. Okay. When exporting, I would use different seam allowances for different reasons. Would have to manually adjust the pattern if I need a 1-inch seam allowance on just one panel. Yes, you have to, and it's very easy to do this. So you could put a global seam allowance on with ExactFlat, and it's very common to use edge offsets for making seam allowances in Rhino. You want to pick an edge. So it's a very easy, very straightforward process to do. And if you want to know more about that, you can just let us know. But any seam allowance with any granularity is possible, and they will be resulting in very well-fitting patterns. Okay, how do you smooth out the Proliner curves before surfacing? This is a great question because the Proliner will do one of two things. It'll capture point data, or it'll capture a line. Actually, you can actually trace lines out with the Proliner. So Luke, can you just talk about how you would smooth a line between points in Rhino?
So let's say you've got a curve here and it looks something like this. That might be your Proliner input. In Rhino, you can just use the curve through polyline command, and that's going to interpolate a curve through that polyline.
And there's a couple of ways you can do it with the Proliner. You could either capture more points or less points. If you have more points, you'll have a more gradual curve, albeit a polyline. But when you run a spline through it, you'll get a much smoother, connection with the surface. So you have a couple of options there. And just to recap our process, your core workflow is 3 steps. You capture the geometry using a Proliner, you create 3D surfaces using Rhino, and you create 2D patterns using ExactFlat. And while we did have a relatively easy project here in terms of the number of surfaces and the curvature of surfaces, I can assure you that if you've got much more complex projects, that you can take this on and you can be very successful. And in fact, ExactFlat and the Proliner and Rhino 3D are in widespread use in the marine industry, both for upholstery, marine canvas, making boat hulls themselves, whether they be metal or carbon fiber, and for engine covers and things like that. And with that, I'm going to say goodbye and close our webinar down. Thanks again, Luke. Thanks everyone from attending, and we hope to hear from you soon.